this plot here corresponds to what this SPHEREx experiment proposed to achieve using the power spectra and using the bispectra of galaxy distribution. And this is a combination. And so, of course, we don't know where the answer would be, but with this kind of accuracy, so the key point here is that we are almost at the one sigma at one level accuracy, so which is the accuracy we want for test common homogeneity. With this kind of accuracy, wherever we land on this plot, when we actually perform this measurement, we will learn something very profound about the nature of inflation. And that's why really some of us are working very hard to make this survey. It should be a dedicated small satellite to do that, and we are working very hard to make it happen. I will skip that and jump to the conclusion. And so, one of the key conclusion, my number one conclusion, I think, is the fact that Planck and the CMB observation program has been extremely successful. Planck as a mission has been very successful, and key cosmological parameters are robustly constrained to surpass accuracy. But of course, Planck is really the last implementation of a very large and worldwide effort by the CMB community, which has spanned over the since its discovery for the last 50 years. Right? And it's not only this big technological breakthrough, but also very, very large theoretical support. It's really a big program has delivered what it promised about a couple of decades ago. And, but there are new questions. This kind of accuracy leads to new questions for cosmology. And one of these questions is, of course, what's the nature of inflation? How did inflation really happen? Or what's the nature of dark energy? I'm not even really start to explain it. And in particular, we know Planck as a success, but we know now we learn more from CMB, but we also learn much more from large-scale structure. And it will be there are many experiments being designed. There's a Euclid satellite, WFIRST, SPHEREx maybe, on ground-based default like this. But to do that, and the thing we want to do, so we want to do wider and deeper large-scale structure survey to measure FNL, spectral index, and running of the spectral index. And also, of course, we want to do better and deeper measurement of the polarization of CMB to understand the scale of inflation. Thank you very much.
Thank you. I'm sorry that you have to cut the CMB lensing part, but I'm sure people will be interested in and can ask you questions. So, questions?
What the non-Gaussianity is basically the correlation between different frequency in the spectrum.
That's right.
And why would a single field inflation lead to non-Gaussianity?
Why would single? Well, yeah. So I guess single field inflation does not lead to non-Gaussianity. That's typical. So it leads to a very small amount of non-Gaussianity, which is typically non-measurable. It would be non-measurable. So at the level of 10⁻³ 10⁻⁴ in terms of FNL. So it would be a very small amount of non-Gaussianity. And for natural, for single field inflation, it would be simply nonlinear evolution. The field is evolving, and you have nonlinear effects that will become important. For single field inflation, you can constrain them. And it's directly related to NS-1. Since NS-1 is very small, then this would be a very small effect. But for multiple field, then most multiple field model will lead to a higher non-Gaussianity.
Yeah, thanks.
More questions?
Could you say a few more words about SPHEREx, like the size of the sample, the redshift range, and how it's actually working?
Okay. How many hours do you have? Okay, I'll show you. Okay, I'll do it. I'll show you a slide after. I'm happy to tell you more. So So it's so SPHEREx will be a fine band photometric survey, a low resolution spectroscopic survey, full sky, so between 0.45 micron and 4.8 micron, and for every pixel of the sky of 6 axons, we'll have a spectrum. So you can think of it as an IFU. It's not an IFU, but you can think of it as an IFU. And so we'll have 300 million galaxies with a redshift of 10% accuracy, all the way to 1.5. And then, according to the graph, the better the galaxy, the better the redshift measurement. And so, if you want exquisite photometric, exquisite spectroscopic, if you want very good redshift accuracy, we are restricted to a redshift, let's say 0.3%, which is what you need for BAO. Then you're restricted to redshift 0.7, 0.8. But if you want to do FNL, you don't need actually for FNL with the wide spectra, you don't need a very exquisite redshift accuracy, so 10%, 5% is good enough, and then we have galaxies all the way to redshift 1.5. And so it's a fine band photometric survey, it's a low resolution spectroscopic survey, and we have 100 frequency elements between 0.45 and 4.7 micron, and for each of them the magnitude is about 19 per frequency element. So I'll show you more after. It's a fine low resolution spectroscopy.
Sorry, what's its current status?
So it's it was proposed as a SPHEREx mission, so in December last December. So SPHEREx is the smallest class of satellites that can do for astrophysics, and it was selected for phase A study last August. And now we are getting ready, working on phase A. We'll submit a new proposal in July, and then if we are selected, we will fly in 2020. It's a status is phase A study right now.
Other questions?
It seems there's always a tension between CFD measurement and other cosmological measurements, such as the Hubble constant,
Yes.
and also the lensing.
Yeah.
So what do you think? And the second question is, when will be the next space mission for CMB?
Okay, so there are tension. So when we say tension, tension is a very fashionable word in cosmology nowadays, right? But we have to remember that the scale of the tension we're talking about, like Joe Moore was saying the other day, is like 2 sigma, between 2 and 3 sigma. So we are talking about first pretty small effect as compared to the situation like a couple of years ago. So I think overall it's very big agreement, and now we are discussing smaller tension. I think for H naught, I think there is no CMB. WMAP is consistent with Planck, and we are in slight tension with a supernovae based measurement. And I don't their analysis has been precise, and there have been criticism on our analysis too. But I think first Planck measurements seem to be very robust, don't change, have not changed between a different release, and again it's consistent with WMAP. So it's hard to, I wouldn't know how to change. I tend to believe CMB, of course, but I think Planck measurements tend to be very robust. For lensing or clusters, I guess that's a more difficult one. And I think for clusters is really the fact that clusters are difficult, and really there are all kind of possible interpretation. Mass measurement is really difficult, and so I think we're not there yet. And it includes a cluster interpretation using Planck as a cluster. So it's also Planck, like everyone else, has the same difficulties. And I think my personal view is like astrophysics, like modeling issues. On the other hand, some people like the fact that there is tension in the high redshift universe, low redshift universe, and maybe tell us something deeper. And so at this point, we don't know. Next generation survey, we are making progress, and in a couple of years we should know. But there's new physics, so we need to understand better the current physics. I'm conservative, I guess. So I tend to favor astrophysical uncertainties.
How about the next CND?
Oh yeah, next CND mission. there are a lot of discussion in the community. So I think the most advanced project right now is Lightbird for future space mission, which is led by JAXA, Japanese space agency, which seems to be the Japanese community seems to be committed. So hopefully it will happen. And then there are discussions in the US, also discussion in Europe. So there were several proposals in Europe that were not successful, but there will be a call again in 2 years, 1 year, and then the European community is trying to get organized. But I think on the US it's also there are discussions, but no clear plan yet. So I think the most advanced project so far seems to be Lightbird, which is doing, which is it's very ambitious and very interesting project for sure.
Questions from students? Well, you are always welcome to ask Olivier questions offline. So if there are no other questions, then let's take this.